Hi, this is Jaisurya. I'm going to solve the sixth question in MAT-104 EndSem assignment. Okay, for sixth question, they're given us in this OD y double dash plus 16y is equal to 4, direct delta of t minus 3 pi, and they're given an information of y of 0 is equal to 0 and y dash of 0 is equal to 0. And they asked us to find what kind of real life phenomenon captured by this delta function. Okay, before that, I'd like to explain a bit about delta function. Delta function is defined as delta of t minus a will be equal to infinity at t is equal to a and 0 at everything else. So the graph would look like somewhat kind of this. Let's say the a is around here, so it will be 0 until it reaches a, then it spikes till infinity, then it goes back to 0, and the area of this region is 1. So I'd like to discuss a few properties about delta function. Integral from 0 to infinity delta of t minus a dt will give you a, and likewise delta 0 to infinity f of t delta of t minus a dt will give you f of a. Then this one is important one, Laplace of f of t minus a will be, as you know, Laplace of any function is integral from 0 to infinity e power minus st, and that function here, that function is it's delta. Here the function is delta itself, delta of t minus a dt. So this will be nothing but e power minus as. As from this property we can say it's f of a. Here f is e power minus st, so it's e power minus as. This one will be using it in the further explanation. Okay, I can say that the delta function as it moves forward will be 0, but once it reaches the a, the whatever parameter that it is, it'll spike to a huge amount, then immediately drops. Okay, so for the a part, I can interpret it as delta function is something which catches a huge change in a small amount of time. So we know something which catches a huge change in small amount of time. In this problem, the phenomenon, I think it is impulse. Impulse is nothing but large force in small time. Yeah, this suits the delta function. Okay, so for B part, as for the graphing goes, we can see that there's no damping because there's no y dash element in the real equation. So I'm considering the spring mass system such as this. So, and there's no damping because there's no y dash term in the equation. So, and I'm assuming that it is starting from rest. So the graph will look somewhat like this. So it will be starting at rest from 0, then it will reach a point 3 pi because the delta function is t minus 3 pi. Then after that it will start the sinusoidal wave, and there will be no change in the amplitude or the frequency because there's no damping. Okay. So it will move forward in that way, and I think the amplitude will be plus 1 to minus 1, yeah, because it's sinusoidal. Yeah. So I can see it in this way, like in this spring mass system, initially it will be at rest, then after it reaches time 3 pi, there will be a huge impulse and it will be moving in a constant SHM of some frequency. Yeah. Okay, now coming to the C part, we have to find the solution of this OD. Like we are taking Laplace on both the sides, so we have Laplace of y double dash plus Laplace of 16y equal to 4 into Laplace of delta t minus 3 pi. Okay, we know that Laplace of any derivative of function y dash is equal to s into Laplace of y minus y of 0. So for finding the Laplace of y double dash, we can use this formula. So it will be s into Laplace of y, here the y is y dash, minus y of 0, so it's y dash of 0. So we can expand this further, this one L of y dash, sorry, Laplace of y dash. So expanding further, we'll be having s square to Laplace of y minus s into y of 0 minus y dash of 0. From these two given information, we can cancel these out because it's a 0. Okay, now we have that Laplace of y double dash is equal to s square into Laplace of y. We can keep this equation. Okay, now finding the Laplace of delta of t minus 3 pi. We know that from earlier derivation, Laplace of delta into t minus a is nothing but e power minus as. Yeah. So Laplace of f of t minus 3 pi will be e power minus 3 pi into s. Okay, now we got these two equations. We can substitute in this equation to find Laplace equation. So substituting s square into Laplace of y plus 16, we can take the 16 out, that's not big deal. Y be equal to 4 into e power minus 3 by s, because Laplace we are substituting this one. Okay, now solving and taking Laplace of y common and sending s square plus 16 to that side. So we'll be left with 4 into e power minus 3 by s divided by s square plus 16. Now to find the value of y, we are going to take inverse Laplace on both sides. So we'll be having y is equal to L inverse, Laplace inverse of 4 into e power minus 3 pi s divided by s square plus 16. Okay, so we are going to use second shifting theorem. So second shifting theorem says that Laplace inverse of any of this form e power as to f into s will be f of t minus a dot u into t of a t minus a, sorry. So using this, if we compare these two equations, we can see that f of s is 4 by s square plus 16, which is nothing but Laplace of ft. equal to 4 by s square plus 16. Now we're gonna take Laplace inverse on this function, this equation. So f of t will be Laplace inverse of 4 by s square plus 16, and we know that Laplace of sine omega t is w by s square plus omega square. Here, by comparing these two equations, we can see that omega is 4, so we can say that f of t will be sine 4t. Yeah. Okay. Now we can write that y of Laplace inverse e bar minus 3 by s into 4 by s square plus 16 as sine 4 into t minus a u of t minus a. Here a is 3 pi, so it is y is equal to sine 4 into t minus 3 pi u into t minus 3 pi. Okay, this will be the solution of the ODE. From this we can plot the graph. So we can see that it will be 0 until it reaches 3 pi. I'm taking this point as 3 pi. After it reaches 3 pi, there will be a huge impulse. From this, like we can see it, like after 3 pi, it will be having a huge impulse. Then it will start to plot a sinusoidal waveform. We can see it right here, and the amplitude will be 1, and here it will be -1. Yeah, we can see that this one is like almost like pretty much the same thing I drew it in the B part. Yeah, so that's it.